Hello everyone. In this video, we'll be covering concepts from the course of Chemistry 1412, also known as General Chemistry 2. The concepts that we're covering in this video are going to be on titration curves, solubility, and solubility of ionic compounds. The first thing we're talking about is acid-base indicators. An acid-base indicator is a weak organic acid whose color differs from that of its conjugate base. The ratio of our weak organic acid divided by our conjugate base is governed by the concentration of our H3O plus of the solution. The indicators can therefore be used to monitor the pH change during an acid-base reaction. The color of an indicator changes over specific narrow pH ranges, a range of about 2 pH units. So this is just a picture of a color change of the indicator bromethyl blue. So our first little flask right here is going to be for pHs less than 6. Our middle one shows a pH between 6 and 7.5. And then finally, our nice blue one over here is going to be for pHs greater than 7.5. So as you see, as the pH changes, we can see a color change between the different flasks. Acid-base titrations. In an acid-base titration, the concentration of an acid or a base is determined by neutralizing the acid or base with a solution of base or acid of known concentrations. So what this means is that, say I have my acid of unknown concentration in my flask, I'm going to titrate it or neutralize it using a burette filled with a known concentration of my base. The little stop clock here is just what you turn that allows the base to turn into our acid. However, it could be reversed. So we could have an unknown concentration of base, and we could titrate it with a known concentration of acid. So it can go back and forth. The equivalence point of the reaction occurs when the number of moles of OH- adds equal to the number of moles of H3O plus originally present, or vice versa. The endpoint occurs when the indicator changes color. The indicator should be selected so that the color changes occurs at a pH close to that of the equivalence point. So many times in your labs, your indicator is going to turn it pink. So the moment you get a slight shade of pink, that's your endpoint, and it should be equivalent to your equivalence point. Calculating the pH during a strong acid, strong base titration. The initial pH, the concentration of H3O plus, should equal the concentration of HA initially, where the pH is equal to negative log of the concentration of H3O plus. The pH before equivalence point, so before you hit that endpoint, the initial moles of H3O plus equals the acid times the volume of the acid times the molarity of the acid. The mole of OH- added equals the volume of the base times the molarity of the base. And the moles of H3O plus remaining is going to be your moles that you initially had of H3O plus minus the moles of OH- that you added. So your concentration of H3O plus will be equal to the moles of H3O plus remaining divided by the volume of acid plus the volume of base, where your pH is still equal to negative log of the concentration of H3O plus. The pH at equivalence point, pH equals 7 for a strong acid-base titration. pH beyond the equivalence point. So your initial moles, pretty much all of these two right here, they're going to be the same as our previous slide. So I'm not going to repeat them. but where it changes is our third point right here. So moles of OH minus excess, so how much we have excess, equals moles of OH minus added minus moles of H3O plus we initially had. So this is when we added too much base. The concentration of OH minus equals the moles of OH minus excess divided by the volume of acid plus the volume of base, where our POH equals negative log of OH minus, and our pH is going to be our 14 minus our POH. So let me show you a brief video that will go more into this topic.
Today we're doing a titration, and we start with 20 mLs of 0.500 molar HCl. So we're starting with a strong acid, and to the strong acid, we're going to add a solution of a strong base. We're going to add a 0.500 molar solution of NaOH. And as we add the base, the pH is going to increase. And we can show this on our titration curve. So we put the pH on the y-axis, and on the x-axis, we put the volume of base that we are adding. So in part A, our goal is to find the pH before we've added any of our sodium hydroxide, so the addition of 0.0 mLs of our base. So if we haven't added any base, the only thing we have present is acid, right? We know that HCl is a strong acid, so it is going to ionize 100%. So if HCl donates a proton to H2O, then we get H3O+, and we would get the conjugate base to HCl, which is Cl-. If we're starting with a concentration of 0.500 molar HCl, let's go ahead and write that, 0.500 molar HCl, and since we know this is 100% ionization because we have a strong acid, that's the same concentration of hydronium ions that we'll have in solution. So we have 0.500 molar for the concentration of hydronium ions. And now it's easy to find the pH because we know that the pH is equal to the negative log of the concentration of hydronium ions. So let's go ahead and do the calculation, right? We take the negative log of the concentration of hydronium, which is 0.500. So that gives us 0.301. So we plug this into here, and we get a pH equal to 0.301. So we can find that point on our titration curve. So it's right here at the beginning, right? We've added 0.0 mLs of base, and our pH looks like it's just above 0 here on our titration curve, and we calculated it to be 0.301. All right, let's find another point on our titration curve. So this time, after we add 10 mLs of our base. So we find 10 mLs of our base right here, and we're trying to find this point, right? So what is the pH after we add 10 mLs, right? Well, it looks like it's pretty close to 1. And let's see if we can calculate what the pH is. All right, so if we're adding base, we know that the base that we're adding, right, the hydroxide ions that we're adding are going to neutralize the hydronium ions that are already present. So first, let's calculate how many moles of hydronium ions that we had present here. So the concentration of hydronium ions is 0.500. So let's get some more room down here. We know the concentration of hydronium ions is equal to 0.500 molar. And we know that concentration, right, or molarity is equal to moles over liters. So if this is the molarity, that's equal to the moles of H3O plus over the liters. So what was the original volume of acid that we started with? Let's go back up here to our problem. We started with 20 milliliters, right? So let's write that right here, 20.00 mLs. If I want to convert that into liters, I move my decimal place 3 to the left. 1, 2, 3. So that's 0.02 liters. So let me go ahead and write that in here. So we have 0.02 liters. And there are going to be a lot of zeros in this video, and it would be annoying if I said them all. So I'm just going to say 0.02 and not list all of those zeros that we have. All right, so to solve for moles, we just multiply 0.5 by 0.02, and so we would come out with the moles of H3O+, and this is equal to 0.01 moles of H3O+. So that's the moles of acid that we're starting with, and we're going to add some base, right? We're adding some sodium hydroxide. And we know sodium hydroxide is a strong base. So the concentration of sodium hydroxide is the same as the concentration of hydroxide ions, right? Na plus and OH minus. So 0.500 molar solution of sodium hydroxide is 0.500 molar for hydroxide ions. So we write down here the concentration of hydroxide ions is equal to 0.500 molar. And once again, we need to figure out how many moles of hydroxide ions that we have. And what's the volume, right? We have 10 milliliters. So in liters, that would be, move our decimal place, 3, right? So that's 0.01. So this is equal to 0.01 for our liters. Solve for moles. So we would just multiply 0.5 by 0.01, and we would get our moles equal to 0.005. Right? So that's how many moles of hydroxide ions we have. All right, now that we've found moles of both our acid and our base, we can think about the neutralization reaction that occurs. Right? The base that we add is going to neutralize the acid that we had present. So we had hydronium ions present, and we added some base. So the acid donates a proton to the base. If OH minus picks up an H plus, then we get H2O. If H3O plus donates a proton, we get another molecule of H2O. So we end up with 2 H2O over here. Or if you prefer, instead of writing H3O plus, you could have just written H plus, right, as your proton, and your proton reacts with hydroxide to give you water. So either way of representing the neutralization reaction is fine. So let's plug in our moles here. So we know that we started with 0.01 moles of H3O plus. So let me write that down here, 0.01 moles of H3O plus. And we started with, we added, I should say, 0.005 moles of hydroxide, right? So we added 0.005 moles of hydroxide ions. All of the hydroxide is going to react, right? It's going to neutralize the same amount of hydronium ions. So we're going to lose all of our hydroxide ions because the base is going to completely react with our acid. So we're left with 0 moles of our base. Right, so if we're losing that much hydroxides, right, we're also going to lose that much hydronium. So that much is reacting with the hydroxide ion. So we're losing the same amount of hydronium ions. Right, so 0.01 minus 0.005 is, of course, equal to 0.005. So that's how many moles of hydronium are left over. Right, so we've neutralized half of the hydronium ions present, and so we have another half left over. Right, so 1/2 of the acid has been neutralized, so 1/2 of the acid is left. Let's think about the new concentration of hydronium ions in solution. So the concentration of hydronium is equal to moles over liters. Right, so that would be 0.005 moles of H3O plus. Well, what is the new volume? We started with 20 mLs of our acid, and to that we added 10 mLs of our base, right? So right up here, we added 10 mLs of our base. So the new volume is 30 mLs, right? We added 10 mLs, and so our new volume is 30 mLs. So to find the new concentration of hydronium ions, we need to use 30 mLs, or 0.03 liters, right? 1, 2, 3. So this would be 0.03 liters. And we can get our concentration. So let's get out the calculator here, and let's take 0.005. We're going to divide that by 0.03, and we get our concentration of hydronium ions to be 0.17, right? So our concentration is equal to 0.17 molar. Now that we know our concentration of hydronium ions, right, so our concentration is 0.17, we can find the pH. Because, of course, the pH is equal to the negative log of the concentration of hydronium ions. So the negative log of 0.17. So we get out our calculator one more time, and we find the negative log of 0.17, and that gives us a pH of 0.77. So our pH is equal to 0.77. So now we know we add 10 mLs of base, and the pH is 0.77. So let's go back to our titration curve up here, right, and find that point we talked about earlier. So we found this point right here after 10 mLs of base. This pH right here is 0.77. All right, so we just did the calculation to show it. On the next video, we'll analyze this titration curve. We'll look at some more points on it.
All right, so that's going to wrap up the video that we had to share, and we'll go back to our PowerPoint presentation. And so hopefully that made titration curves and how to actually do calculations with titration curves a little bit easier when you're dealing with a strong acid and a strong base. Calculating the pH during a weak acid, strong base titration. So now we're doing a weak acid in place of a strong acid. The initial pH, so we have Ka is going to be equal to the concentration of H3O plus times A minus divided by HA, where the concentration of H3O plus is going to be equal to the square root of Ka times the HA initial, where the pH is equal to negative log of the concentration of H3O plus. Before the equivalence point, so our H3O plus is equal to Ka times our concentration of HA divided by A minus, or we can say that pH equals pKa plus log of our base divided by our acid. pH at equivalence point. So this is going to be the general formula that we can use. So we have A minus plus water yields HA plus OH minus, where our OH minus concentration is equal to the square root of Kb, so B for base, times our concentration of A minus, where A minus equals the moles that we initially had of HA divided by the volume of acid plus the volume of base. Kb equals Kw, which is a constant, divided by Ka. The concentration of H3O plus is going to be near, so not completely equal, but pretty close to Kw divided by the square root of Kb times Ka. And we can still use the equation of pH equals negative log of H3O plus. pH beyond equivalence point. So this is past that, it's when you add a little bit too much on your titration, we pass that equivalence point. So the concentration of OH minus is going to be equal to the moles of OH minus excess, so how much more we put in, divided by the volume of acid plus the volume of base. And the concentration of H3O plus will be our Kw divided by the concentration of OH minus. And our pH is still going to be equal to negative log of H3O plus. So now we have an example to where we're trying to compare and contrast different titration curves. So it says, which one of the following is the best representation of a titration curve which will be obtained in the titration of a 0.1 molar weak base with HCl of the same concentration? So let's think about what we know. We know we start with a weak base, which means we can't have A or B. So if you look at the pH is too high initially to be dealing with a weak base. So A and B cannot be our answer. So we're stuck between C, D, and E. E isn't a proper titration curve. You simply are like decreasing. So E, we know we can cancel out, so we're now stuck between C and D. So we have a 50-50 chance. For C, what we have is a titration with a weak acid. So this is going to be a weak acid because we have a weak curve. And then D is going to be titrated with a strong acid. And so we have to look at the acid that we're dealing with. We're dealing with HCl. HCl is a strong acid, which means that C would not be our answer and D would be the answer choice that we go with. So we look, see where it starts, we see how strong that curve is, and then that should tell us which titration curve to pick. Titrating a weak acid with a weak base or vice versa. This is going to depend on the magnitude of your Ka and Kb. This is an important concept to know, which is why I gave it its own slide. Equilibria of slightly soluble ionic compounds. Any soluble ionic compound is actually slightly soluble in an aqueous solution. We assume that the very small amount of such a compound that dissolves will dissociate completely. For a slightly soluble ionic compound in water, equilibrium exists between the solid solute and the aqueous ions. So now we have an example down here. So we have PbF2, our solid, yields Pb2 plus 2F minus, both of which are aqueous. And then our QC is going to be our Pb2 plus times our F2 to the, F minus squared divided by PbF2. So the concentration of our products divided by our reactants, where our QSP is going to be our QC times our PbF2, which is also equal to the concentration of our products multiplied by each other. QSP and KSP. QSP is called the ion product expression. So that's what we were talking about before, for a slightly soluble ionic compound. For any slightly soluble compound, this is just going to represent compounds right here. So MP times XQ, which consists of ions of M to the N plus and X to the Z minus, where QSP is going to be the concentration of M to the N plus, where this P right here is now our coefficient, and XZ minus is going to be to the Q, which was the number right here. So these letters are just going to be representing numbers in an actual compound that you're dealing with. When the solution is saturated, the system is at equilibrium, and KSP and QSP are equal to each other. The solubility of the product constant, so that is our KSP. The KSP value of a salt indicates how far the dissolution proceeds at equilibrium, or saturation. So let's go through an example. 1 liter of saturated silver chloride solution contains 0.00192 grams of dissolved AgCl at 25 degrees Celsius. Calculate KSP for the AgCl. So let's go to our boogie board so that we can work this out. So the first thing we need to do is to write out our equation or our reaction. So we have AgCl solid yields Ag plus aqueous plus Cl minus aqueous. And so we need to find the KSP for our AgCl. So we know that KSP is going to be equal to the concentration of just plus, so no 2, so plus, times Cl minus. And we don't have any numbers here, so nothing really changes. So we need to know what goes into the slots to give us our KSP. And what we need to do is to figure out how many moles of these compounds we have, and then we multiply them and we'll get our KSP. So the first thing we need to do is we take the grams that they gave us of our AgCl, and we have to get it to moles of AgCl to compare it to our broken down compound. So we had 0.00192 grams of AgCl. We can set up a table for every 1 mole of AgCl. We have 143.35 grams, and this is just going to be the weight from that periodic table. So our grams will cancel out, and we'll get 1.34 times 10 to the negative 5 moles, and this is going to be moles of AgCl. We can now use this to compare to both the Ag plus and the Cl minus. So we have 1.34 times 10 to the negative 5 moles of AgCl. And we know that for every 1 mole of AgCl, we have 1 mole of Ag plus. So we end up with 1.34 times 10 to the negative 5 moles of Ag plus. And what you'll notice is that with both of them, we're going to have a 1-to-1 ratio. So it's going to be the same. So we'll have 1 mole of Ag here, and then we'll also do the same thing for 1 mole of Cl, which means that we have 1.34 times 10 to the negative 5 moles of Cl minus. But you can set it up the exact same way and it'll give you the same answer. However, it's not always going to be set up like this. It's not always a 1-to-1 ratio. So make sure you do the math when you have more than one compound. So we now have it in moles, but to plug it in, we have to have it in molarity. But because they told us that we had 1 liter solution, and molarity is moles per liter, so you divide both of these by 1, and you'll end up getting it in molarity. So we can use these numbers to plug in here. So we say that KSP equals 1.34 times 10 to the negative 5 times 1.34 times 10 to the negative 5, and we'll get a KSP of 1.80 times 10 to the negative 10, and this is going to be our KSP value. Okay, and now let's go ahead and work through another example. And this time, they want us to calculate the solubility product constant for lead-2 chloride if 50 milliliters of a saturated solution of lead-2 chloride was found to contain 0.2207 grams of lead-2 chloride dissolved in it. So we take into consideration our grams, our volume, and what we're looking for. So they kind of wrote it out this time instead of saying solve for KSP, but it's pretty much the same thing that we're looking for. So we're looking for the KSP of PbCl2. So just like before, we need to write out our equation. So we say PbCl2 solid yields Pb2 plus aqueous plus 2Cl minus aqueous. And it's pretty much the exact same steps that we took last time. So we know we need to find this, it's going to be Pb2 plus and Cl minus to the 2 to be able to get our KSP. So the first thing we need to do is get moles of our full compound. So we take the 0.2207 grams of PbCl2, we set it up, and for every 1 mole of PbCl2, we have 278.1 grams. Our grams will get canceled out, and we'll end up with 7.936 times 10 to the negative 4. This is going to be moles of PbCl2. This is a 4. And so now we can use our moles of our compound to compare to get moles of Pb2 plus and Cl minus. So we take 7.936 times 10 to the negative 4 moles of PbCl2, set up our table, and for every, let's do Pb first. So for every 1 mole of PbCl2, we have 1 mole of Pb2 plus. So we have 7.936 times 10 to the negative 4 moles of Pb2 plus. And now we need to find moles of Cl minus. So 7.936 times 10 to the negative 4 moles of PbCl2. For every 1 mole of PbCl2, we have 2 moles of Cl minus. So 2 moles Cl minus. So we'll end up with 1.5872 times 10 to the negative 3 moles of Cl minus. But we can't quite plug it in here. We have to convert this from moles to molarity. So we know that we have 50 milliliters, which we have to convert to liters. So you'll do 7.936 times 10 to the negative 4 moles divided by 0.05 liters, and we'll get 0.0159 molar Pb2 plus, and then we do 1.5872 times 10 to the negative 3 moles divided by 0.05 liters, and we'll get 0.0318 molar of Cl minus. We can now plug these in to our equation up here. So let me erase this real fast because I ran out of room. So we can say our KSP equals our molarity of our Pb2 plus, which was 0.0159, times our molarity of Cl minus, which was 0.0318, and that had a squared up here. So when you plug this in, your KSP will be equal to 1.61 times 10 to the negative 5, and that would be your answer. Now we're going to talk about the effect of pH on solubility. Changes in pH affect the solubility of many slightly soluble ionic compounds. The addition of H3O plus will increase the solubility of a salt that contains an anion of a weak acid. And so we have CaCO3 solid yields Ca2 plus CO3 2 minus. And so what happens is we get CO3 2 minus plus H3O plus, which is our acid, yields HCO3 minus plus H2O. So we have HCO3 minus plus H3O plus yields the concentration of H2CO3 plus water, which yields CO3 plus 2 water. The net effect of adding the H3O plus to the CaCO3 is the removal of CO3 2 minus ions, which causes the equilibrium to shift to the right. The more CaCO3 will dissolve. Predicting the formation of precipitate. For a saturated solution of a slightly soluble ionic salt, our KSP and 2SP will be equal. When two solutions containing the ion of a slightly soluble salt are mixed, if our QSP and KSP are equal, the solution is saturated and no change will occur. If our QSP is greater than our KSP, a precipitate will form until the remaining solution is saturated. If our QSP is less than our KSP, no precipitate will form because the solution is unsaturated. And so if you're trying to think of what a precipitant is, it's going to be, let's say if we have a glass of water and we add salt into it, and you're sitting there stirring it, if our QSP and our KSP are equal, no change will occur. If our QSP is less than our KSP, it means that we don't have enough salt for the salt to remain. So the solution is unsaturated. We have more water than we do salt. And then for QSP is greater than KSP, we're going to see that the salt or the precipitant is forming at the bottom. And that pretty much covers everything that we're covering in this video. So let's do a brief overview of everything that we talked about. The first thing we talked about was acid-base indicators. And this is going to be the color change based off the pH. So think about your pH strips. pH strips are an acid-base indicator. Also, the phenolphthalein that you add in a titration is also going to be considered an acid-base indicator because once you hit that endpoint, it turns pink, and that's when you know your titration has ended. Acid-base titrations, we covered both strong acids and strong bases, and strong acids and weak bases, in both of which you were able to see a titration curve, and we were able to work an example on how to tell which titration curve belongs to a certain set. And then finally, we covered solubility of ionic compounds, where we talked about QSP, which is the ion product expression, and KSP, which is the solubility of product constant. And then you were able to actually work two examples where we solved for KSP. So that wraps up everything we have today. I hope that this video was helpful. Thank you and good luck on these topics.